All right, welcome back. Let's continue our discussion of definite integrals today with properties of definite integrals. So these are going to be super important for the rest of the class and super important if you're going to Calc 2 especially. So let's look at the first one. A zero width interval. So this makes sense. And some of these will make intuitive sense. Some of them are not so intuitive. But a zero width interval, this says that the definite integral from a to a of f of x dx is 0. Well, okay, think about that. I mean, if you think about if you have a function, you know, and you want the definite integral from a, and like you stop and start at a, okay, of course, like if you have a to b, obviously you have a region there, and you're finding the net area of that region. But if you don't have a b that's to the right, like you just have a to a, like a is on top of itself. Well, like imagine there's no net area there. Okay, now we can show it's true using the limit definition. Here, let's look at that real fast. Just like with all of our derivative property limits, we can use the derivative properties. We could use the limit definition of the derivative to show those true. Here, we can use the limit definition of the definite integral to show this property is true. So if we want to show the definite integral from a to a of f of x dx is 0, well, let's use the limit definition. Okay, so according to the limit definition, this is equal to the limit as n goes to infinity of a appropriate Riemann sum. Now, of course, I didn't specify what function we're talking about. That's not specified at all. However, we don't need that. This works for any function where the function's integrable. But what's delta x? We can always calculate delta x as b minus a over n, where b is the right-hand side of your interval, a is the left-hand side. Well, if b equals a, you stop and start at a, well then the delta x is calculated as a minus a over n, 0 over n, which is 0. So delta x is 0. And now let's think about this. If you have the sum, these are all y values, function values. If you have the sum of a product of a function value times 0, plus another function value times 0, plus another function value times 0. If you're always multiplying the function values times 0, and then you're adding up all those terms, you just get 0. So that's why you have the limit. That's why you have a zero width interval always has a definite integral of 0. Easy peasy. Now here's one that's not so intuitive, but it's very important, especially if you're trying to use geometry to evaluate a definite. So this one says if you swap the limits of integration, if you want to look at the integral from b to a instead of a to b, then it's the opposite. Okay, really important. This does not make a lot of geometric sense. But let's just think about this. Here's what it's saying. So this does not make a lot of intuition. But if you want to take the definite integral from a to b, you get that. You get the net area. But if you instead take the definite integral from b to a, you get the opposite of net area. Now I can show you why this is true from the limit definition of the definite integral. Now let's take a look. So if you want to show, if we know that we start with this, okay, the definite integral from a to b of f of x dx, well, we know what the limit definition says. It says you take the limit as n goes to infinity of an appropriate Riemann sum. Okay, where what? Where delta x is b minus a over n. So that's the only thing I did in the next line. But remember, b minus a over n, that means that b is the right-hand side and a is the left-hand side. Okay, well, what if you want to rearrange this? What if instead you let a and b swap places by factoring out a negative sign? Okay, so we factor out a negative sign, and now that puts a minus b on the numerator, but you have a negative out front. But what can we do with a negative? What can you do with a constant and a sum? You can factor a -1 out of a summation. In fact, you can factor a constant out of a summation, and you can factor a constant out of a limit. So not only can we take that constant -1 and put it there, we can do better than that and actually take out the constant and take it outside the limit, because we have a constant multiple rule for limits and summations. So we factor that -1 out, and now we have a minus b. Okay, well again, this is your right, and that's your left. So now a is the right, and b is the left. And so we get the definite integral with b on the left. Sorry, with b on the left and a on the right. But guess what? We had that negative sign out front. And so that's where it comes from. Now, why would we use this? Oh, occasionally we'll have the situation where maybe we're trying to use geometry, but here's something I haven't noticed before. I haven't told you before because I haven't had the occasion to tell you. If you want to use geometry, you have to have the situation a is less than b. So I'll just jot down. To use geometry to evaluate the definite integral from a to b of f of x dx, a must be less than or equal to b. Okay? I suppose if they're equal to each other, you get a 0 with the interval and you get 0. Okay? But basically, if you want to use geometry, a has to be the lesser value. But let's say you have a situation where you want to use geometry and that's not the case. Well, we can swap the limits and just introduce a negative sign out front. In fact, we'll probably have an example like that sooner or later where we will do just that. Okay? Let's see what else we have. We have the sum and difference. Okay, the rest of these should be pretty straightforward. I'll talk about number 5 a little bit. Constant multiple rule. Okay, we've had a constant multiple rule of limits. We've had a constant multiple rule of derivatives. We've had a constant multiple rule of antiderivatives. We've had a constant multiple rule of summations. And now we have a constant multiple rule of definite integrals. So there's 5 different constant multiple rules, but they all behave the same way. You can factor out a scalar multiple, a constant multiple, out of a derivative, out of an antiderivative, out of a sum, out of a limit, and out of a definite integral as well. Sum and difference. This just says if you have the definite integral of 2 terms. In fact, it works just like with derivatives. If you have lots of terms, you can take all the definite integrals individually, just like you take all of the derivatives individually. Okay, so we're familiar with that. That property is intuitive. You could take the antiderivatives. Now this is only for sums and differences. For products and no such luck. Products, quotients, and such, no such luck. But for sums and differences, addition or subtraction, you can take the definite integral of the terms individually. Now the last example here is what I call the additivity property. And this makes geometric sense, but it also doesn't make geometric sense sometimes. But here's what it says. If you want the definite integral from a to b of f of x dx, that's equal to the definite integral from a to c f of x dx plus the definite integral from c to b of f of x dx. Now here's the intuitive side of it. Imagine we have some function blah blah blah, and we have a over here, and we have b over here, and imagine c is right there. This says if you take the definite integral from a to b, from a to c, you get that. And then if you take the definite integral from c to b, you get the rest. And if you add it up, Well, you get the definite integral of the entire thing, which makes sense. You know, you're talking about like decomposing the region into two regions, two disjoint regions, and if you add them together, you get the whole thing. So that's kind of like the intuitive approach. But here's the weird approach. So it makes sense like that, right? But notice in property 5 or in like in like the setup to the theorem, let k be a constant and f be integral in AB, it specifies nowhere that C has to be between A and B. So this makes geometric sense quite nicely if C is between A and B. But what if you have the situation like this? So we have some function, and we have A. Oh, let's put B right here and C right there. Guess what? The property still holds. And that's what's kind of funny. Now I can show you why it still holds. Now here's what it says. It says if you take, if you have the definite integral from A to B of f of x dx, this is certainly equal to the definite integral from A to C of f of x dx plus the definite integral from C to B of f of x dx. So even if C is not between A and B, it still works. So this will be like if you take this definite integral from A to C, you get that, and you add the definite integral from B to C. Oh, sorry, we did what from A to C, yeah, and then from C to B. You get the definite integral from A to B. Now, why is that? And I think that hopefully my picture might give you a little hint, and I'll walk you through the formality of it. Notice if I want to use geometry to evaluate the definite integral from C to B, what must I do? Notice what is the case here. B is to the left of C. Okay, so what must I do in order to use geometry? I would have to reverse the limits of integration and say, put a negative sign out front, and that way, at that point, it would make geometric sense because I would have the definite integral of the whole thing from A to C minus the definite integral of the blue region gives me the definite integral of the region from A to B. And that's where we're going here, because additivity, it works whether A is less than B is less than C, whether C is less than A is less than B is less than C. It doesn't matter the order at all. The additivity property works, and it doesn't immediately make geometric sense, but it does eventually if you remember that in order to use geometry, you have to have A is less than B for a definite integral, and if not, you have to reverse the signs. Okay. Here's the formal proof. So if you suppose that A is less than B is less than C, that is, C is to the right of B. Okay, well, you know that the integral from A to C is equal to the integral from A to B plus the integral from B to C. Okay, if you rearrange this a little bit, so if you subtract the integral from B to C, so subtract this from both sides, subtract and take to the other side. It's just a number, so you can do that. You get this next line. You get the integral from B to C, the definite integral from B to C being subtracted off. However, if B is less than C, okay, we could swap the limits of integration, and we get the definite integral from A to C, and we get a double negative there because we swapped these limits of integration by the limit reversal property. And so double negative ends up being positive, and then we have the definite integral from a to c plus c to b, and that gives us exactly what we were looking for. Exactly what we were looking for in our property, that from a to b, the integral from a to b is equal to the integral from a to c plus the integral from b to c. Okay, cool. All right, let's use these properties. Let's use these properties in a few different contexts. So, example 4.5.2, integral from pi to pi of cosine x dx. All right, we have not talked about definite integrals in trig yet. However, doesn't matter. Why? Because we have the integral from a to a, from pi to pi. So, remember, the only condition for evaluating a definite integral is the function has to be continuous. And we know that cosine x is certainly continuous. So we know there has to be an answer out there. Now, if we had a situation where we did not have the limits are the same, but we'd be stuck right now. Now we'll talk about that pretty soon, about how to do trig functions with definite integrals, but we don't know how to do that yet. So for us right now, we're lucky us because we know that we're doing a zero width interval here. So the answer has to be 0. Again, because we're going from the definite integral from a to a. This is a 0 width interval. So the answer has to be 0. Okay. Now, remember, we only have 2 options for evaluating definite integrals right now. We have geometry, and we have the limit definition. So we could certainly use the limit definition, right here. I don't really want to use it on C, but we could use it on B if we wanted to. But I think we can use geometry to be quicker. Remember, geometry is usually the quickest if it affords itself, but usually it doesn't afford itself. But it does here. Let's think about this. But remember, well, let's just draw a picture first. So here, let's just see 2x. That's a slope of 2 and a y-intercept of 0. So it's a line that basically looks like that. Okay. Now, 0 to 4 is the region we're concerned with. So it's this. But remember, if you want to use geometry, what must be true? A must be less than or equal to B. There is A, and there is B. A is not less than or equal to B. But how can we remedy that? We could remedy that by saying, all right, the original is the definite integral from 4 to 0 of 2x dx. We want to use geometry. So if we swap 0 and 4, now A is less than B, but we have to put a negative sign out front. And now, this can be thought of, this integral, that can be thought of as area, as net area, and we can calculate that using geometry. Now, we can actually think about it as area because that function is non-negative from 0 to 4. So we could simply say this equals, now there's a negative sign out front, of course, negative. 1/2 is a triangle, so 1/2 b. What's the base here? Well, from 0 to 4, that's a base of 4. What's the height? 1/2 base times height. Well, we've seen this before. To find the height, you simply find the y value above 4 right there. So you plug in a 4 into your function, 2 times 4, and we get that point right there is 4, 8. So the height is 8. So we get 1/2 times 4 times 8, which is what, 16? Oh, but there's a negative out front, so negative 16. So be careful. You will have, I'll have a fair number of homework questions that might pop up that might have a situation where geometry is the quickest way to solve, or maybe a test question or exam question for that matter, where geometry might be the best way to solve, but the value of A is not less than or equal to the value of B. So before using geometry, you have to swap them, but that means you have to introduce a negative sign out in front of your definite integral. Because if you reverse the limits of integration, you have to introduce a negative sign in front of your definite integral. Okay, what about C? Oh, let's see here with C. You know, I know what the absolute value of 4 looks like. Sorry, absolute value. And I suppose we know what the absolute value of what the 4 times absolute value looks like. But, you know, let's just say for some reason you don't remember what 4 times absolute value looks like. Like you remember that absolute value is a V, but you don't remember what 4 times absolute value is. Now, of course, if you remember your algebra, this won't be a problem either way. Let's just say for the sake of argument, you don't remember what 4 does. Well, we could say this is equal to, you can factor out a 4 because 4 is a constant multiple, and then we say 4 times the definite integral from -2 to 2 of absolute value of x dx. And now you say, okay, I remember what absolute value looks like. Absolute value looks like a v. Now, it turns out 4 times absolute value of x is just like a skinnier v. It rises quicker to the left and right. But let's just say you don't remember that because you didn't pay attention to algebra class. Okay? So now we could say 4 times whatever our answer is according to geometry. Because, you know, a here is less than or equal to b. So you have, you know, -2 over there, 2 right there. And so we're concerned with this region like so. We have 2 triangles. Okay, so we need to add up the area because this function obviously is non-negative. Absolute value is non-negative. We need to add up the regions. And by the way, I guess technically what we're doing here is we're going to say, hey, technically this is like the definite integral from -2 to 0 absolute value of x dx plus the definite integral from 0 to 2 f of, oh, not f, you can say absolute value of x dx, because we're going to take those, we're going to find those triangles areas individually. Okay, so 4. Now, okay, what's the, it turns out they're identical triangles because of the symmetry of absolute value. So let's see, well, the base is obviously 2, so you have 1/2 times 2. Now what's the height? Well, what's that point right there? What do you get when you plug in -2 into the absolute value? Well, you get -2, 2. So the height is 2. And the base is 2 for both of those triangles. So you have 1/2 times the base 2 times the height 2 plus an identical triangle, 1/2 times the base 2 times the height 2, which is what? 4 and 1/2 times 2 is what? 2 for each of those areas, because you have 1/2 times 4, so 2. But you have 2 plus 2 because there's 2 of them, and so you get 8. All right, so again, you know, that wasn't a hard example, but I wanted to show you how, you know, we're factoring out the 4 because it's a constant, and we're using the additivity property to say, hey, we can take the definite integral of that first triangle and the second triangle individually, and then add up and then multiply by 4. Okay? Last example, oh yeah, let's do these. The last 2 examples, they're pretty straightforward. You know, here we have a given set of of definite integrals. So we have from 1 to 5 of f of x dx is 6, and then the definite integral from 1 to 5 of g of x is -2. So we have 2 different functions, but we're talking about the same interval. And let's just use properties of limits to figure these out. Okay, with a, notice we want the definite integral from 5 to 1. Okay, from 5 to 1, well, we know that we have a limit reversal property. So we can say the definite integral from 5 to 1 of f of x dx, that is equal to the definite integral from 1 to 5 of f of x dx with the negative sign up front, right? Because I swapped the limits of integration, I transposed them, so I need to introduce a negative sign. But here's the thing, the reason I did that is because I know what the definite integral from 1 to 5 is of f of x, it's 6. So it equals negative 6. So the limit reversal property did the job there. All right, what about b? So we have the definite integral from 1 to 5 of 3 times f of x dx. Okay, again, I'm trying to use the two integrals I know about. I know the definite integral from 1 to 5 of f is 6, and the definite integral from 1 to 5 of g is negative 2. Well, what about 3 times the definite integral, or 3 times f, definite integral? Well, it's a constant. I can factor out the 3. So this is 3 times the definite integral from 1 to 5 of f of x dx. And again, I know what the definite integral from 1 to 5 is. It's 6. So this is 3 times 6, 18. Oh, what about c? Well, c, the definite integral from 7 to 7 of g of x. Okay, well, I don't really know anything about 7 to 7 except that, oh, it's a zero width interval. 7 to 7. We're stopping and starting our region on top of itself. So there is no region. It's a zero width interval. So this has to be 0. Again, 0 width interval. It's going to be 0. Okay, and now what about example D? Oh, example D. Okay, this is a tougher one, but we're going to still use the basic same properties we used in these examples. We have from 1 to 5. We have, let's see, 4 times f of x plus 1/2 times g of x minus 5 dx. Okay, what have we not used yet? We haven't used the sum difference rule yet. So we can take the definite integrals of each term individually. So this is the definite integral from 1 to 5 of 4 times f of x dx plus the definite integral from 1 to 5 of 1/2 g of x dx plus the definite integral from 1 to 5. Oh, sorry, that's a minus. I lost a negative sign. Minus the definite integral from 1 to 5 of 5 dx. Okay, and remember, I only have 3 things to work with. I have that, and I have that. Sorry, I have 2 things to work with, not 3 things. And of course, I have my properties. So I need to factor out a 4 out of this first one. 4 times the integral from 1 to 5 of f of x dx plus factor out a 1/2. It's a constant. So 1/2 times the definite integral from 1 to 5 of g of x dx. And now this last one, well, I don't have anything to help me there except that, oh, it's a constant function. I got geometry to help me there. So minus, I'm just going to leave it as 1 to 5 of 5 dx, and we'll use some geometry here in just a minute. All right, 4 times the definite integral from 1 to 5 of fx dx. Oh, that's equal to 6 from our given information. Then 1/2 times the definite integral from 1 to 5 of g of x. Oh, well, we know it's negative 2. So times negative 2, 1/2 times negative 2. Minus integral from 1 to 5 of 5 dx. Well, you tell me. 5 is a constant function. So if there is 5, and we want the definite integral from 1 to 5, well, what do we have? Looks to me like we have a nice old rectangle. With what? A base of 4 and a height of 5. So base times height. So minus rectangle area, base times height. 4 times 5. Equals, let's see, what, 24 plus 1/2 times negative 2. So that would be minus 1 minus 20. So 24 minus 21. Looks to me like we get a nice 3. Cool. Okay. Cool. So that's properties of definite integrals. Properties of definite integrals. So you want to make sure to commit these to memory. We talked about a few of them. We talked about what? 4 or 5 of them. Yeah, 5 of them. So zero width, limit reversal. Both of those are very important. Constant multiple. We'll use that all the time. Sum and difference all the time. Additivity. Yes, all the time. So all of those we will use on a very, very regular routine basis for the rest of the class. And if you're going to Calc 2, even more so there. So make sure to really commit these to memory, print them off and have them when you're doing your homework so you can really apply these because they will be necessary for pretty much most of the problems we're working now throughout the rest of the class. Okay? All right, we'll catch you in the next video. We'll do some more examples using these properties videos. As always, reach out if you need help. I'll talk to you soon.